In this lesson, we're going to learn about exponential growth and decay models. A mathematical model is an equation that is designated to mimic a pattern observed in real life. Many equations in physics, chemistry, or economics are created based off of mathematical observations that were transformed into a model. The model that we are concerned with in this section is called the exponential growth and decay model. In many applications where populations grow or decay at very rapid rates, such as in radioactive decay, compounding interest, or population growth, this model does a very good job at describing these types of changes. The model is y equals y sub 0 e to the kt, where y sub 0 is called the initial population size, E is the constant value 2.71828 that we've been using thus far in the course. K is referred to as the growth or decay constant, and if K is positive, it'll be a growth constant, so the population is increasing in size. And if K is negative, it will be a decay constant, so the population is decreasing in size. T is a period of time, which is usually years, but it doesn't have to be in years. And y is referred to as the new population size. A lot of times we'll use this model as a function, so you may see me express it as y of t equals y sub 0 e to the kt, and this is the exact same model. I'm just expressing it as a function so that I can plug in some amount of time that's passed in order for the population size to grow. It means the same thing. Now, as an example problem, let's suppose the population of a culture of bacteria grows according to the following exponential model. Y equals 1.54 e to the 0.1586 times t, where t is measured in days and the initial population size is in millions. How many bacteria will be present after 7 days? Well, the number of bacteria present will be the new population after 7 days. So y represents the new population size, t is going to be 7 days. So y of 7 is the population after 7 days. Equals 1.54 e to the 0.1586 times t, which I'm going to allow to be 7. And there isn't much solving that's necessary here. All we really need to do is plug this into a calculator, and that will tell us the estimated population size. So here is the calculator, and let's figure out what this is going to be. So 1.54 times e raised to the, and I need the 0.1586 times 7 all up in the exponent, so I just make sure not to close parentheses until the end. So 0.1586 times 7, and then close parentheses. And I'll round this to 2 decimal places since the initial population size was to 2 decimals. So this would be approximately 4.67. The initial population size was in millions, so approximately 4.67 million bacteria present after the 7 days. Okay, let's look at the next example. How long will it take for the population size to reach 12.5 million? So this time it's going to be a little bit more complex. We'd still be working with the exact same model, y equals 1.54 e to the 0.1586t. The only difference is we're not plugging in a value for t, we're plugging in a value for the resulting population size. So this 12.5 million is going to get plugged in for the value of y. So I'm just going to replace 12.5 for y. And that's what it's going to look like. In order to solve this, the very first thing that I'm going to need to do is divide both sides by 1.54. It's a good idea, especially when you're doing online homework, to make sure that you're not rounding anything until you get to your final answer. Like for instance, if I did 12.5 divided by 1.54 at this point, I would probably take that value 8.116 blah 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 and round it to 8.12. But every time you round an answer, you're introducing error into your calculation. So it's a good idea to just try and prevent any sort of calculation or rounding until you're ready to get your final answer. So for instance, I'm just going to leave this part as 12.5 over 1.54. And that's now going to equal e to the 0.1586t. I know it's going to be approximately 8.12, but I just don't want to round it yet. And that's fine. We just treat it as a normal number. I now need to continue solving my problem, which has a variable up in the exponent. So I'm going to have to change this into a logarithmic equation. So when I change it into a logarithmic equation, I'll do an ancillary step over here. It's going to be a log of the base, which is e, of the 12.5 over 1.54 equal to the exponent, 0.1586t. Now, when I call it an ancillary step, when I'm changing something into a log base e, it makes a whole lot more sense just to go ahead and change that into a natural log. So the next step is going to look like natural log of 12.5 over 1.54 equals 0.1586t, which appears like I'm trying to take the natural log of both sides, and I kind of am, but when you do the natural log of e to the 0.1586t, it just reduces down to the exponent anyway. But the next step is to divide both sides by 0.1586. So that t, let me get a little bit more space here. T is going to be the natural log of 12.5 over 1.54 divided by 0.1586. Now I can plug that into the calculator, because once I get this answer, that's my final answer. So natural log 12.5 divided by 1.54. Notice that division is all inside the argument, so I'm not doing two separate logarithms. It's not like the change of base formula, that is. And then that's divided by 0.1586. So now I get 13.20. And this is an amount of time. And the original unit for the amount of time was days. So this would be 13.20 days. That's how long it would take to reach 12.5 million. Here's another example. According to the 2000 census, a small rural town has a population of 890 people. During the 2010 census, the population has increased to 1,075. If current trends continue, what should the population be in 2020? Well, the very first step we need to do here is solve for the value of k, which is our growth constant. Generally, when you get k, rounding to 4 decimal places is common, unless you have a bunch of leading zeros, which you might need to just make sure you have at least 2 or 3 significant figures. But that shouldn't happen in this case. So let's just show you how to solve for k at this point. All right, so the model that we're working with, you do need to know this model. Y of t is y sub 0 e to the kt. So same one we started with in the beginning. We know that the initial population size is 890. So I'm going to substitute y sub 0 for 890. And after 10 years, so when we go from 2000 to 2010, so after 10 years passed, so I'm going to change the amount of time into 10 years, the new population size is 1075. So this is equal to 1075. Now there's a unique value of k, our growth constant, that will make this work, which we need to solve for. In order to do that, I'm going to have to change it into a logarithmic eventually, but for right now, the first step is to divide both sides by 890. Okay, so I can get e to the 10k is what I'm going to write it as by itself. Now, that's going to look like 1075 over 890 equals e to the 10k. Now, changing that into logarithmic form, I would be doing a log base e, which would be a natural logarithm of this fraction here, and that's going to be equal to the exponent, which is 10 times k. And what you're going to find is these steps may seem tricky at first. There may seem like there's a lot of work, but they're almost always the same steps every single time. Because here, even though I'm solving for k instead of t like we were in the last example, when I divide both sides by 10, I get k is equal to the natural log of 1075 over 890 divided by 10, which allows me to approximate that growth constant. And I bet my calculator's in the perfect spot. I thought I was going to hide my formula here. Wonderful. Natural log of 1075 over 890 divided by 10. So it looks like I have 0.018885, which I'm just going to round to, I think I'll use 4 decimal places because I said 4 decimals is common, so I'll just use that. 0.0189. And if your homework says to use 3, follow those instructions, obviously. All right, so now that makes my model look like y equals 890 e to the 0.0189 t. So that's my model for growth. There was 2 parts to this question, really. So, well, actually there was 1 part to the question, but the first step involving solving that problem was to solve for k. So we've come up with k, we have our growth model. Now I want to know if the current trends are continuing, what should the population size be in 2020? All right, so let's answer that part. All right, so let me make sure I have plenty of space to write here. So my model, let me copy it back down over here. 890 e to the 0.0189 t. I want to know what the population size in 2020 is going to be. Well, this model was set up based off of a number of years from the year 2000, because the population size was 890 in the year 2000. 10 years later, it was 1,075. And we based that off of just an increase of 10 years rather than the actual value of 2010. So I guess what I'm saying is, what I'm not going to do, and I'll do this in red because I'm going to erase it, it's wrong, is try and do y of 2020 and plug 2020 in for t. Because that would be 2020 years past the year 2000. So I would be looking at the year 4020. And this model's probably not going to be accurate to that distance away. I'm actually going to do y of 20 because 2020 is 20 years away from 2000. So that's what I'm looking for, that population size. Okay, so it would be 890 e to the 0.0189 times 20. And I don't need to solve for an exponent, so I can just plug everything into the calculator. So let's bring that up. Clear out what I have already. So 890 e raised to the 0.0189 times 20. So I'll round to the nearest whole number just because we're talking about population size and people. So 1,299, which makes sense because, you know, in 10 years we saw an increase of, you know, approximately 200 people, and so in the following 10 years it's about the same. A little bit more because it's an exponential increase, but about the same. So it's about the same. So it's about the same. Okay, let's move on to another example. The half-life of carbon-14 is approximately 5,700 years. Use this fact to determine the approximate age of a mammal that is discovered trapped in ice and containing 15% of its, and we don't need an apostrophe, do we? I'll edit myself there. Original amount of carbon-14. Well, carbon-14 dating, the way this works is there's an amount of carbon-14 that's present in nature, you know, at any point in time, which through ice core sampling you can determine what that amount is. And using that, you can take an object, see how much carbon-14 is left in the object, because it's a radioactive element. It decays away after it dies, because it's not taken on anymore. And you can use that comparison to get the approximate age of the object, or, you know, living being. Well, non-living anymore. The process is basically the same of what we did in the last example. We first need to figure out the value of k. So we need to solve for k, which is our, in this case, it's going to be a decay constant, so it's going to be a negative number. But we base this off of the same model we've been using. So y of t equals y sub 0 e to the kt. And let's plug in what we know here. So the population size after 5,700 years, if I just plug in 5,700, I would get y sub 0 e to the k times 5,700, which leaves a lot of variables left in this problem. But here's something that we can count on. after 5,700 years passes, when we're talking about the half-life of a radioactive object or a radioactive element, that means half of that element's mass is going to decay away. So after 5,700 years, the mass of, or the amount remaining is going to be half of the original amount. So I'm going to take y of 5,700 and replace it with 1/2 of the original amount. So it actually doesn't matter what the original amount is precisely, because the only thing we're concerned with in half-life is that half of it's going to decay away after a certain period of time. So if this initial amount happened to be 100 grams, 5,700 years passes, now there's 50 grams. Another 5,700 years passes, now there's 25 grams. It's just going to decay by half of the original amount each 5,700 years. So if you take this equation and divide both sides by y sub 0, it just cancels out on both sides, leaving you with 1/2 equals e to the 5,700 times k. Using that, which is an equation with only one variable remaining, we can change it into a logarithmic equation, so it would be a log base e, or a natural log, of 1/2 equals the exponent, which is 5,700 times k. And then I just divide both sides by 5,700. So natural log of 1/2 over 5,700. I can now put that into the calculator and come up with an approximation. So in this example, natural log of 1/2, or I could put 0.5, that's fine, either way, divided by 5,700. I get negative 1.216, and then some extra digits, then I have e minus 4. That e minus 4 is just the way that the calculator represents scientific notation. So essentially this is representing negative 1.216 times 10 to the negative 4th power. Or you would have 3 leading zeros and then start your significant digits. So I'll put it as 122. Or actually, I think the examples I did, I only did 0.12, so I'll leave it as 0.12. For problems that you're working in the homework, follow the rules of rounding there. But for this example, I did just use 0.1, 0.00012, which is fine. Now, the next thing is that now let's go on to the next part of this problem, which is to determine the approximate age of this mammal that was trapped in ice. So in order to do that, let me make sure I have enough space here. We need to take what we just learned and plug that into our model. So our model now looks like y of t equals y sub 0. We still don't know that original amount of carbon-14. E to the negative 0.00012 t. And it's still okay that we don't know the original amount of carbon-14, because we know that there's 15% of the remaining amount. So I'm sorry, 15% of the original amount. So 15% of the original amount, 15% of y0 that is just 0.15 times y0. So that's the ending amount. So this thing now has 15% of its original amount. Which the original amount divides away again. And once it divides away, we have a problem that we can readily, easily solve here. So I would need to change this into a logarithm. So it would be a log base e, which is a natural log, of 0.15 equals negative 0.00012t. So t is equal to, in this case, the natural log of 0.15 over negative 0.00012, which from the calculator is, turn it on here, oh, it's not functioning. Okay, so natural log 0.15, oops, divided by negative 0.00012. I have, let's just go to the nearest year here, I suppose. 15,809 years. So that's the approximate age here. Here's another example. This is continuously compounding interest. And if you've ever worked with interest equations, you've seen probably have seen the continuously compounding interest formula, which is a equals p e to the, actually that should be an r, p e to the r times t. And it actually looks extremely similar to the model that we've been using, y equals y sub 0 e to the kt. And that's absolutely true. It's basically, it is the exact same model, just with different variables. So if you want to use a equals p e to the rt, that's fine. Or if you just want to use the same model we've been using throughout, that's okay as well. Either way is fine. The first question here wants us to find out the amount of time it will take an investment to double in value at an interest rate of 6.5% compounded continuously. So our model is a equals p e to the rt. R is our interest rate, which is the exact same thing as what we've been using for the growth constant. P is the principal, which is the exact same thing as the initial amount present. And A is the ending amount, which is the same thing we've been using as Y. So we have an investment, and we don't know exactly what the starting amount is, but we know that we want it to double. So we want whatever we start with, we want to end with double that. So 2 times the initial amount is our ending amount. Then e to the interest rate's 0.065, and the time here is just a variable left as t. So similarly to how the carbon-14 example worked, this initial amount actually just divides away. So p cancels out, and I have 2 equals e to the 0.065 t, which I can change into a logarithmic equation. It would be a log base e, which is a natural log, of 2 equals 0.065 t. So that means t is going to be, sorry about that, the natural log of 2 divided by 0.065, and I will do that on the calculator. So the natural log of 2 divided by 0.065, and I've got 10.66, I'll just say approximately 10.7 years. There's no need to try and change that into months and days and things. Just in these examples, just leave it as the decimal. 10.7 is fine. The next example, if $28,000, sorry about that, is invested in a 401k earning 4.8% interest, how much is in the account after 5 years? So still using the same basic formula, A equals PE to the RT. The initial amount is $28,000. The interest rate is 4.8%, so I changed that into a decimal, of course, 0.048. And we want 5 years to pass. Nice thing about this particular problem is that the variables are all filled in, and all I need to do is just plug stuff into the calculator. I don't need to do any particular solving here. So 28,000 e raised to the 0.048 times 5. So it's going to be 35,594.98. And that's the amount in the account after 5 years passes.